Good evening and welcome back to the Late Lab. I'm very glad you've joined me. Before we settle into tonight's subject, let me know where you're listening from. Perhaps you're tucked beneath the covers, watching the lights pass by from a late train, or simply winding down somewhere quiet after a long day. Wherever this finds you, I hope the room feels peaceful, the night feels gentle, and you can let your thoughts slow down for a while. Should these calm journeys through science help you relax, a like and a subscription are wonderful ways to support the channel. And if you're already part of this little late night community, thank you for returning. Every view, comment and quiet evening spent here helps the Late Lab continue. Tonight, we're exploring a property with one of the most misleading names in physics. Quantum spin sounds as though electrons and other particles must be whirling around like microscopic planets or tiny spinning tops. But that picture, useful as it may first appear, is not what nature is actually doing. Spin is something stranger, deeper, and far more important than simple rotation. So, let's ease into it. What is quantum spin? And how can something possess angular momentum without truly spinning at all? Quantum spin begins with a name that seems to explain everything, right up until it explains almost nothing at all. The word spin invites a very familiar picture. It suggests a tiny object turning around an internal axis, rather like a planet rotating through space, a wheel turning on an axle, or a toy top circling on a table. For a time, physicists wondered whether particles such as electrons might behave in something like this way. Perhaps the electron was a minuscule charged sphere, physically rotating and producing its magnetic effect through motion. That picture is no longer accepted. Fundamental particles are not believed to be tiny solid balls with little surfaces spinning around hidden axes. An electron does not contain an equator rushing through space, nor does it have identifiable pieces circling around a center. As far as modern experiments can determine, the electron behaves as an elementary point-like particle, yet it still possesses a property called spin, and this property is every bit as real as its mass or its electric charge. Spin is therefore best understood as an intrinsic quantum property. The word intrinsic matters because it means the property belongs to the particle itself. It does not arise because the particle is travelling along a curved path, orbiting something else, or physically turning. An electron carries spin wherever it goes. It has spin while moving through empty space, while resting within the limits allowed by quantum theory, and while bound inside an atom. This makes spin fundamentally different from ordinary rotation. A football may spin quickly, slowly, or not at all. Its rotation can be altered continuously. An electron does not possess an adjustable amount of intrinsic spin in that sense. Every electron in the universe has the same spin magnitude. An electron inside a laboratory instrument on Earth has the same intrinsic spin as an electron inside a distant star, a cloud of interstellar gas, or a galaxy billions of light years away. The electron belongs to a class known as spin 1/2 particles. This does not mean that the electron completes half a rotation or rotates at half a particular speed. It refers to the mathematical rules governing its intrinsic angular momentum and the measurement results that quantum mechanics permits. This is where the misleading name begins to recover a little of its usefulness. Although spin is not ordinary rotation, it behaves mathematically like angular momentum. Angular momentum is the conserved quantity associated with rotation. A spinning wheel has angular momentum. A planet orbiting a star has orbital angular momentum. Quantum particles can also carry angular momentum in several forms, and intrinsic spin is one of them. Spin can be transferred between systems. It can combine with orbital angular momentum. It can affect how atoms exchange light. It can contribute to the total angular momentum of a particle collision. When the spin state of one object changes, another part of the system may gain or lose angular momentum so that the total remains conserved. Nature treats spin as genuine angular momentum, even though no tiny mechanical rotation lies beneath it. Spin also produces magnetic effects. The electron has an intrinsic magnetic moment, which allows it to interact with magnetic fields. In some ways, this resembles the magnetic behavior of a rotating charged object. A spinning distribution of electric charge would create both angular momentum and magnetism, so the early name was not chosen at random. It captured a real resemblance. The difficulty appears when the resemblance is treated as a literal description. A map can resemble a landscape without being made of soil and trees. In much the same way, the mathematics of a rotating object can resemble certain aspects of quantum spin without revealing a microscopic spinning mechanism. The analogy is useful for predicting some effects, but it breaks down when pushed too far. There is another distinction that often causes confusion. An electron has a fixed total spin magnitude, but a measurement of spin must be made along a chosen direction. A magnetic field might define an upward and downward direction, for example. When the electron is measured relative to that axis, quantum mechanics permits one of two outcomes, commonly called spin up and spin down. These names do not mean that the electron is physically rotating clockwise or anti-clockwise. They describe the result obtained for one component of its spin along the selected measurement direction. Change the direction of the measuring apparatus, and the possible outcomes are defined relative to the new axis. The fixed property and the measured component are therefore not the same thing. The electron always possesses its characteristic spin magnitude. What may vary is the outcome obtained when one part of that spin is measured along a particular direction. This unusual property reaches into almost every corner of quantum physics. Spin helps determine how electrons arrange themselves inside atoms. Those arrangements create the structure of the periodic table and influence chemical bonding. The collective behavior of electron spins contributes to magnetism in materials. Nuclear spin makes nuclear magnetic resonance possible and supports the medical imaging techniques used to examine the human body. Spin also helps classify elementary particles. It separates matter particles from force-carrying particles and influences the statistical rules they obey. It appears in entanglement experiments, where the spin measurements of distant particles can display correlations that no ordinary classical model can reproduce. Modern researchers also use spin states in quantum sensors, experimental quantum computers, and devices that control information through magnetism. All of this emerges from something that is not, in the usual mechanical sense, spinning. Quantum spin is one of the clearest reminders that the microscopic world cannot always be understood by taking a familiar object and making it smaller. An atom is not simply a miniature solar system. An electron is not a tiny charged marble. And spin is not an invisible top rotating very quickly. Sometimes nature preserves part of a familiar pattern, while abandoning the picture that once made the pattern easy to imagine. Spin carries angular momentum, creates magnetic effects, and obeys precise rules associated with rotation. But the particle itself is not physically whirling around an internal axis. The name remained. The spinning did not. Long before physicists began speaking about quantum spin, they already knew that rotation carried something important. A turning wheel does more than move. Once it is spinning, it tends to preserve both its motion and its orientation, unless an outside influence changes them. A bicycle wheel held by its axle can feel strangely stubborn when someone tries to twist it sideways. A spinning top resists falling for a while. A planet turning on its axis keeps its orientation with remarkable steadiness, while a moon travelling around a planet carries a different kind of rotational motion. The physical quantity behind this behaviour is angular momentum. Angular momentum is the rotational counterpart of ordinary momentum. Linear momentum describes motion along a path, while angular momentum describes motion associated with rotation around an axis or a point. Like ordinary momentum, angular momentum is conserved. If no external torque acts on a system, the total amount remains unchanged. This conservation law appears everywhere. A figure skater pulls in their arms and spins faster because the same angular momentum is concentrated into a smaller distribution of mass. A collapsing star can rotate more rapidly for a similar reason. The cloud of gas that formed the solar system carried angular momentum, and part of that ancient motion survives in the planets orbiting the Sun. Classical physics recognizes two familiar forms. An object may rotate around its own axis, as Earth does once each day. An object may also travel around another body, as the Moon moves around Earth. The first is rotational angular momentum, while the second is orbital angular momentum. Earth carries both because it rotates while orbiting the Sun. Physicists naturally wondered whether microscopic matter might behave similarly. Perhaps tiny charged constituents were circling, rotating, or doing both. When electric charge moves in a loop, it creates a magnetic field. A circulating current therefore behaves like a tiny magnet and possesses what physicists call a magnetic moment. A rotating distribution of charge can carry angular momentum and magnetism at the same time. This suggested a mechanical explanation for magnetic materials. Perhaps the magnetism of iron and other substances came from countless microscopic currents circulating inside matter. André-Marie Ampère developed an early form of this idea during the 19th century. He proposed that magnetism could arise from tiny closed electric currents within materials. Atoms and electrons were not yet understood in their modern form, but Ampère had identified an important relationship. Moving electric charge could create magnetic behavior. The connection became even more interesting when physicists studied the light emitted by atoms. A hot gas does not usually emit every possible color with equal strength. Instead, it produces sharp spectral lines at particular wavelengths. Each element creates its own distinctive pattern, rather like a signature written in light. In 1896, Peter Zeeman placed glowing atoms in a magnetic field and found that certain spectral lines split into several nearby lines. This became known as the Zeeman effect. The results showed that the systems producing atomic light were sensitive to magnetism. Atoms were not featureless points. They contained charged motion, or magnetic structures capable of responding to an external field. Hendrik Antoon Lorentz helped explain the effect using classical electron theory. In this picture, charged particles inside atoms moved in ways that produced radiation and magnetism. An applied magnetic field altered their motion, changing the frequencies of the emitted light and separating one spectral line into several components. For some patterns, the classical explanation worked well. It strengthened the belief that microscopic angular momentum and magnetic moments were deeply connected. Yet other splitting patterns proved harder to explain, warning that the classical picture was incomplete. The connection between magnetism and visible mechanical rotation became clearer in the Einstein-de Haas effect. Albert Einstein and Wanda Johannes de Haas investigated what happened when the magnetization of a suspended metal cylinder was reversed. As the internal magnetic state changed, the cylinder began to rotate slightly. Angular momentum had been transferred between the microscopic magnetic system and the ordinary mechanical motion of the cylinder. The experiment showed that whatever changed inside the material carried real angular momentum. When that internal angular momentum shifted, the larger object responded so that the total remained conserved. This made the later word spin seem reasonable. If microscopic magnetism behaved as though it came from rotating charge, perhaps the charged particles inside matter really were spinning. The idea carried the confidence of classical physics. Wheels spun, planets spun, rotating charges could behave like magnets. The pieces appeared to fit together neatly. Nature, however, had withheld one important detail. Classical objects can point in any direction. A tiny magnetic needle may be tilted a little, a great deal, or anywhere in between. If atoms contained ordinary rotating charges with randomly oriented axes, Their angular momenta and magnetic moments should form a continuous range of orientations. Atomic measurements began to reveal something different. Instead of allowing every possible result, nature appeared to permit only particular values. Microscopic angular momentum did not behave like a collection of miniature spinning tops. Its measurable components arrived in separated steps. The classical connection between charge, rotation, and magnetism had revealed something genuine, but it could not explain this restriction. Atoms carried angular momentum and responded to magnetic fields, yet their measured outcomes refused to spread smoothly across every possible direction. The image of microscopic spinning had led physicists towards the right mystery, but it had not given them the right answer. Atomic light was one of the first clear signs that the microscopic world was refusing to behave like an ordinary mechanical system. When a solid object is heated until it glows, it can produce a broad spread of colours. Atoms in a thin gas behave differently. When they are excited and their light is passed through a prism or diffraction grating, the result is not usually a continuous rainbow. Instead, bright lines appear at sharply defined wavelengths, separated by dark gaps. Each chemical element produces its own characteristic pattern. Hydrogen displays one arrangement of lines, sodium another, and iron a much denser collection. These spectral fingerprints became powerful tools for identifying substances in laboratories and in distant stars, but they also created a serious theoretical problem. Many classical models suggested that electrons inside atoms should be able to move with a continuous range of energies. If that were true, atoms ought to emit a broad range of frequencies. Instead, they released and absorbed light only in particular amounts. Nature appeared to be selecting certain possibilities, while quietly refusing all the others. In 1913, Niels Bohr proposed a model of the hydrogen atom that placed this selectiveness at its centre. He imagined the electron occupying only certain permitted states around the atomic nucleus. An electron could move from one state to another by absorbing or emitting a specific quantity of energy. The frequency of the emitted light depended on the difference between the two allowed energies. This connected the discrete structure of the atom to the sharp spectral lines measured in experiments. Bohr's model captured several important features of hydrogen with remarkable success. It explained why the atom could remain stable and reproduce the main pattern of hydrogen's spectrum. Yet the picture still relied on electrons travelling around the nucleus in definite paths that resembled miniature planetary orbits. Those paths were restricted by quantum rules, but they remained classical in appearance. The model also struggled when physicists turned to atoms containing more than one electron. Helium was already difficult. Heavier elements produced intricate spectra that could not be organised using Bohr's original rules alone. Arnold Sommerfeld expanded the model through what became known as the old quantum theory. Circular electron orbits were joined by elliptical ones, and additional quantum numbers were introduced to distinguish different possible forms and orientations of motion. Sommerfeld also included corrections inspired by Albert Einstein's special theory of relativity. These refinements explained some of the finer details seen in hydrogen's spectrum. They showed that energy levels previously treated as identical could be divided into closely spaced sublevels. Even so, the growing collection of rules began to look less like a complete physical theory and more like a carefully maintained set of repairs. The difficulty became especially obvious when atoms were placed in magnetic fields. In the normal Zeeman effect, a spectral line divides into a simple and orderly pattern. The behaviour can be understood by considering the orbital angular momentum of an electron and the magnetic moment associated with its motion around the nucleus. An external magnetic field changes the energy slightly depending on the orientation of that orbital angular momentum. The normal effect was encouraging because it appeared to support the classical connection between moving charge, angular momentum, and magnetism. Unfortunately, many atoms produced more complicated splitting patterns. These were grouped under the rather unhelpful name anomalous Zeeman effect. The word anomalous did not mean that the experiments were unreliable. It meant that the results did not fit the available explanation. Some spectral lines split into unexpected numbers of components. Their spacing and relative positions could not be reproduced using orbital angular momentum alone. The atoms behaved as though the electrons carried an additional magnetic and angular momentum property, but no accepted model described what that property might be. Alfred Landé helped bring order to these puzzling measurements. He developed what became known as the Landé factor, a numerical quantity describing how strongly a particular atomic state responds to a magnetic field. The Landé factor successfully organized many of the complicated spectral patterns. It related the total angular momentum of an atomic state to its magnetic behavior and allowed experimental results to be predicted with increasing accuracy. Yet the calculation worked before its deeper physical meaning was understood. The equations seemed to know that something extra belonged to the electron, even while physicists remained unsure what that something was. It was a little like possessing a reliable recipe for a dish, containing an ingredient that no one had yet identified. Wolfgang Pauli confronted the problem while studying how electrons were arranged inside atoms. In 1924, he proposed that the electron possessed a two-valued property that could not be described using ordinary classical mechanics. Pauli was deliberately cautious. He did not initially describe the property as a rotating electron. He referred to it as a classically indescribable two-valuedness. That phrase was not especially elegant, but it was honest. The evidence required two possible states, while every familiar mechanical picture seemed likely to create more confusion than clarity. This additional two-valued property helped resolve another major puzzle. Atomic electrons occupied states described by several quantum numbers, but the observed structure of the periodic table suggested that each permitted combination could accommodate only a limited number of electrons. In 1925, Pauli formulated the exclusion principle. It stated that no two electrons within the same atom could occupy a state described by exactly the same complete set of quantum numbers. Two electrons could share the same spatial orbital, but they required different values of the mysterious two-valued property. One could occupy one possibility, and the other could occupy the second. Once both were present, no third electron could enter that identical orbital state. This principle explained how electrons fill successive atomic shells rather than all collapsing into the lowest available energy state. It helped account for the repeating structure of the periodic table and the chemical behavior of the elements. The missing property was therefore doing far more than adjusting a few spectral lines. It was helping organize matter, yet its physical nature remained obscure. The old quantum theory could identify patterns, construct useful rules, and assign numerical values, but it could not provide a consistent picture of why electrons possess this additional two-valued freedom. Spin entered physics through this gap. No one had watched an electron rotate. No experiment had revealed a tiny surface turning around a microscopic axis. Instead, atomic spectra, magnetic splitting, and electron arrangements demanded an additional form of angular momentum. The evidence came first. The name and the imagery followed later. What physicists eventually called spin was not discovered by seeing something spin. It was inferred because atoms repeatedly behaved as though electrons carried an intrinsic quantum property that classical motion could not supply. In 1922, in the German city of Frankfurt, Otto Stern and Walter Gerlach carried out an experiment that would become one of the defining demonstrations of quantum physics. At the time, the modern idea of electron spin did not yet exist. Physicists were still trying to understand how angular momentum behaved inside atoms, and whether its orientation could take any value or only certain permitted ones. Stern and Gerlach designed a practical test that allowed nature to answer. Their apparatus began with a small oven containing silver. When heated, the silver produced a stream of neutral atoms. The escape through narrow openings that shaped the stream into a thin beam, rather like light passing through a sequence of slits. The beam then travelled through a specially designed magnetic field. The field was not uniform. One side was stronger than the other, creating what is called a magnetic field gradient. That unevenness was essential. A uniform magnetic field can alter the orientation of a magnetic moment, but a field gradient produces a net force. An atom whose magnetic moment points one way is deflected towards the stronger region, while an atom with the opposite orientation is pushed differently. After passing through the field, the atom struck a detecting surface. Over time, a visible deposit of silver formed wherever they arrived. The shape of that deposit revealed how the magnetic field had affected the beam. Silver atoms were useful because they are electrically neutral. Each contains positively charged protons and negatively charged electrons, but its total electric charge is zero. This prevented ordinary electric deflection from overwhelming the subtler effect produced by the atom's magnetic moment. Classical physics offered a clear expectation. If the atomic magnetic moments behaved like tiny compass needles with random orientations, then some would point strongly along the magnetic field, some strongly against it, and many would lie at every possible angle in between. The field gradient would deflect each atom by an amount depending on that orientation. The detector should therefore have shown a continuous smear, with atoms landing across a broad range of positions. That is not what happened. The silver beam separated into two distinct regions. Instead of filling the space between them with a smooth spread of impacts, the atoms gathered into two separated bands. The result showed that the measured component of the atom's angular momentum could not take every possible value. Along the direction selected by the magnetic field, only two outcomes appeared. This became known as space quantization. The phrase described the surprising fact that angular momentum did not seem free to point in any arbitrary direction when measured. Nature permitted particular results rather than a continuous range. The Stern-Gerlach experiment was not originally designed as a direct measurement of electron spin. In 1922, George Eugene Uhlenbeck and Samuel Abraham Goudsmit had not yet proposed the electron's intrinsic spin. Stern and Gerlach were investigating predictions connected with the old quantum theory and the quantization of atomic angular momentum. Only later, as quantum mechanics developed, did physicists understand why the silver beam divided into two. A silver atom contains 47 electrons. 46 occupy filled inner arrangements, whose angular momentum contributions largely cancel in pairs. The remaining outer electron occupies a ground state with no orbital angular momentum, but it still possesses intrinsic spin. Because of that unpaired outer electron, the silver atom behaves effectively as a spin 1/2 system in this experiment. When its spin component is measured along the direction defined by the magnetic field, two results are possible. These are commonly called spin up and spin down. The names are convenient, but they can revive the wrong picture. They do not mean that the electron is a small ball rotating upwards or downwards. They describe two possible outcomes for one component of intrinsic angular momentum along a chosen axis. The total spin magnitude is fixed. Every electron possesses the same intrinsic spin magnitude. Yet a measurement does not reveal a little arrow with every possible orientation. It returns one of the permitted component values relative to the apparatus. The atom therefore carries a definite overall amount of intrinsic angular momentum, while the result obtained along one selected direction comes in discrete steps. The magnetic field does not discover a continuously adjustable classical tilt. It separates the beam according to the quantized values allowed by quantum theory. The force responsible is also clear. The atom possesses a magnetic moment associated with its angular momentum. As it passes through the uneven magnetic field, the interaction between that moment and the field gradient pushes the atom in one of two directions. The detector turns an invisible quantum property into two visible deposits of silver. This is why the experiment became so famous. It made quantization appear not merely as a mathematical rule, but as a physical separation that could be seen on a surface. Even so, the experiment did not photograph an electron rotating. It did not reveal a microscopic axis, a physical surface, or tiny pieces circling around a center. Nothing in the apparatus observed literal spinning motion. What it revealed was more subtle. An atom's intrinsic magnetic moment interacts with a magnetic field gradient in a way that produces discrete measurement outcomes. The atom behaves as though it carries angular momentum, because it truly does carry angular momentum, but the underlying property is quantum mechanical, not a miniature version of a spinning top. The silver atoms entered as one narrow beam and left as two. In that simple division, the continuous expectations of classical physics gave way to the restricted possibilities of the quantum world. By 1925, the evidence was becoming difficult to ignore. Electrons seemed to carry a form of angular momentum that could not be explained by their motion around the atomic nucleus alone. Yes. George Eugene Uhlenbeck and Samuel Abraham Goudsmit were young Dutch physicists studying under Paul Ehrenfest at Leiden University. While trying to understand Wolfgang Pauli's mysterious two-valued property, they proposed that the electron itself possessed an intrinsic angular momentum. This was not angular momentum created by an orbit or by motion through space. It belonged to the electron as part of its basic identity. Their proposal gave a physical interpretation to an idea that had previously been introduced mainly as a rule. Pauli had shown that electrons required an extra two-valued distinction in order to make sense of atomic structure and the exclusion principle. Uhlenbeck and Goudsmit suggested that this distinction was connected to a new kind of angular momentum carried by the electron. The idea helped explain several stubborn features of atomic spectra. Electrons in atoms responded to magnetic fields as though they possessed magnetic moments beyond those created by orbital motion. Spectral lines split into patterns that ordinary orbital angular momentum could not fully reproduce. If the electron carried its own angular momentum and magnetic moment, many of those puzzling patterns became easier to organize. The first image attached to the proposal was simple and appealing. Perhaps the electron was a tiny charged sphere rotating around its own axis. A rotating object carries angular momentum, and a rotating distribution of electric charge can create a magnetic moment. The picture seemed to join the two required properties in one neat mechanical model. It was also exactly the sort of picture classical physics encouraged. Planets rotated, wheels rotated, charged currents produced magnetism. If an electron behaved like a very small charged ball, then spinning it appeared to offer an obvious explanation. Paul Ehrenfest encouraged Uhlenbeck and Goudsmit to publish their idea. They knew that more experienced physicists had serious doubts, and they worried that the proposal might be too crude. Ehrenfest recognized that even an imperfect idea could be worth placing before the scientific community. At the very least, the objections would reveal where it failed. Their concern was justified. Hendrik Antoon Lorentz quickly pointed out that a literal spinning electron created severe problems. If the electron were an extended sphere with a physical surface, it would need to rotate extraordinarily quickly to produce the measured angular momentum. For a sufficiently small electron, parts of that imagined surface would have to move faster than light. That would conflict with Albert Einstein's special theory of relativity, which does not allow material objects or signals to exceed the speed of light. The classical model also struggled with electrodynamics. A rotating charge body produces electromagnetic fields, and its distributions of charge and mass must behave consistently. Attempts to construct a stable mechanical electron had already produced difficulties. Adding the required rotation made the picture even less convincing. There was another problem. The relationship between the electron's angular momentum and its magnetic moment did not match the simplest classical expectation. The measured magnetic effect was roughly twice as large as the most straightforward orbital model suggested. This became known as the factor of two problem. That discrepancy mattered because the spinning sphere was meant to explain angular momentum and magnetism together. If the numerical relationship between them was wrong, the picture was not merely incomplete, it was pointing in the wrong mechanical direction. The story became clearer through the work of Llewellyn Hilleth Thomas. While studying spin-orbit coupling, Thomas identified an additional relativistic effect now called Thomas precession. Spin-orbit coupling describes an interaction between an electron's intrinsic magnetic moment and the electromagnetic conditions associated with its motion inside an atom. Early calculations produced a result that was too large by a factor of 2. Thomas showed that the electron's changing motion required an extra relativistic rotation of the reference frame used to describe it. Thomas precession corrected the discrepancy in the atomic calculation. It did not rescue the image of a rigid electron physically spinning like a ball. Instead, it showed that relativity had to be handled carefully when intrinsic angular momentum interacted with orbital motion. The proposal by Uhlenbeck and Goudsmit therefore survived, but not in its original mechanical form. What endured was the claim that the electron possesses an intrinsic degree of freedom, carrying angular momentum and a magnetic moment. What faded was the belief that this property could be explained by a tiny surface rotating around an internal axis. A scientific idea can contain a correct structure and an incorrect picture at the same time. The language of rotation connected the new property to angular momentum, magnetic effects, and the two possible outcomes appearing in experiments. Yet the image that first made the idea intuitive was not the mechanism nature was using. The word spin remained because it captured enough of the mathematics to be useful. The property transformed like angular momentum, contributed to magnetic interactions, and could exchange angular momentum with other systems. By the time a deeper theory arrived, the term had already become part of physics. Modern quantum mechanics does not treat electron spin as literal rotation. Paul Adrian Maurice Dirac's relativistic theory would later show that spin one-half behavior emerges naturally from the mathematical structure required to describe electrons consistently with special relativity. The electron needs no surface, internal axle, or hidden pieces moving in circles. Its spin is intrinsic. It is part of what an electron is. The early spinning sphere was a productive analogy, not a successful physical mechanism. It guided physicists towards a genuine property while giving them a picture they eventually had to abandon. Science often works this way. A name survives, an image fades, and the underlying idea becomes more precise. Spin kept the vocabulary of classical rotation, even after physics discovered that nothing inside the electron was literally turning. The simplest way to test the old picture of electron spin is to take it seriously for a moment. Imagine that the electron is a tiny charged sphere. Suppose this sphere rotates around an internal axis, rather like a microscopic planet. Its rotation would carry angular momentum, while the moving electric charge would produce a magnetic moment. At first glance, this seems to explain both of the important properties associated with spin. The difficulty begins as soon as the size of the imagined sphere is made sufficiently small. An ordinary rotating object carries angular momentum because its mass is distributed through space and moving around an axis. The amount depends partly on how fast the object turns and partly on how far its mass lies from the centre. A large wheel can carry substantial angular momentum without rotating at an absurd speed because much of its mass is located some distance from the axle. A very small object has much less room to work with. If the electron were a tiny sphere, producing its measured angular momentum would require its surface to move extremely quickly. As the assumed radius becomes smaller, the required surface speed rises. In simple classical models, the speed soon exceeds the speed of light. That result is immediately troubling. Albert Einstein's special theory of relativity does not allow material parts of an object to move through space faster than light. A rigid charged sphere rotating at such a speed could not be a physically acceptable electron. This argument is often presented as the decisive proof that the electron cannot literally spin. It is a useful warning, but it should not be pushed too far. The calculation begins by assigning the electron a classical size, a rigid surface, and an ordinary distribution of mass and charge. Modern physics does not claim that any of those assumptions describe an electron. The faster-than-light surface is therefore not a complete derivation of what the electron truly is. It shows that the classical spinning sphere is internally inconsistent when forced to reproduce the electron's measured properties. The model fails its own test. Experiments provide an even stronger reason to abandon the picture. Physicists have examined electrons using high-energy scattering, in which particles are accelerated and directed towards one another so that their interactions can reveal structure at extremely small scales. The principle is similar to using shorter wavelengths of light to resolve finer details, although particle accelerators reach scales far beyond ordinary microscopes. So far, experiments have found no evidence that the electron contains smaller components, an extended mechanical surface, or a measurable internal radius. Within present experimental limits, it behaves as an elementary point-like particle. Point-like does not necessarily mean that the electron is a tiny bead of zero size hiding somewhere in space. It means that the standard model of particle physics does not describe it as a composite object with detectable internal parts. The electron is represented by a quantum field, and what we call an electron is an excitation of that field. Its spin belongs to that field excitation intrinsically. There are no smaller pieces inside the electron circling around an axis. There is no material shell whose equator can race through space. Nothing needs to rotate mechanically in order for the electron to possess angular momentum or a magnetic moment. This becomes clearer when spin is compared with ordinary rotation. A classical object can be spun faster or slower. Its angular momentum changes when its rotation rate changes. A flywheel may begin at rest, accelerate, and later slow down as friction removes energy and angular momentum. The intrinsic spin magnitude of an electron does not behave this way. Every electron has the same fixed spin magnitude. Accelerating an electron through a laboratory does not make it acquire a larger intrinsic spin. Slowing it down does not reduce that spin. Changing its translational motion through space is not the same as winding up an internal rotor. An electron may exchange angular momentum with its surroundings, and its spin state may change relative to a selected direction. Yet the type of particle remains the same. It does not become a more strongly spinning electron simply because it moves faster. This distinction also separates intrinsic spin from orbital angular momentum. Orbital angular momentum arises from the spatial structure of a quantum state relative to a chosen point or another object. An electron bound within an atom can occupy a state whose wave pattern has orbital angular momentum around the nucleus. That property depends on how the state is distributed through space. Intrinsic spin does not arise from that spatial orbit. An electron can possess spin even in a state with no orbital angular momentum at all. The outer electron in the ground state of a silver atom provides a useful example. Its relevant orbital angular momentum vanishes, yet its intrinsic spin remains. Modern physics therefore replaces the spinning ball with a more precise description. Spin is defined by the way a quantum state transforms under rotations. It is governed by the algebra of angular momentum. It determines which measurement results are allowed along a chosen direction. It contributes to magnetic interactions, conservation laws, particle statistics, and the combination of angular momenta in larger systems. These statements may sound more abstract than a tiny turning sphere, but they describe what experiments actually reveal. The electron responds to rotations in a specific quantum mechanical way. It carries a fixed intrinsic angular momentum. Its spin component along a selected axis can produce discrete measurement outcomes. Its magnetic moment interacts with external fields. None of this requires a hidden mechanical surface. The temptation to picture literal spinning is understandable because the property shares real features with rotational motion. Spin is conserved as angular momentum. It can be transferred. It can combine with orbital motion. It can influence magnetism. But a shared mathematical role does not imply a shared physical mechanism. The electron does not spin through space like a wheel or a planet. It possesses a quantum property that takes part in nature's rules for rotation. The rotation is in the structure of the theory, not in the turning of a tiny ball. Once the image of a tiny rotating ball has been set aside, spin can be described more accurately as intrinsic angular momentum. The word intrinsic means that the angular momentum belongs to the particle itself. It does not arise from the particle travelling around another object, following a curved path, or occupying an orbit around an atomic nucleus. An electron possesses spin even when its quantum state has no orbital angular momentum at all. This distinction separates spin from the more familiar orbital form of angular momentum. Orbital angular momentum depends on the spatial structure and motion of a system relative to a chosen point. The Moon carries orbital angular momentum because it travels around Earth. An electron in certain atomic states carries orbital angular momentum because its quantum wave pattern is distributed around the nucleus in a particular way. Intrinsic spin requires no such path. It is one of the defining properties that identifies the kind of particle being described. Quantum mechanics represents measurable physical properties using mathematical objects called observables. Position is an observable. Momentum is an observable. Energy and angular momentum are observables as well. Each observable is associated with an operator, which acts on a quantum state and determines the possible results of a measurement. Those results are not always free to take any value whatsoever. In classical physics, the angular momentum of a rotating wheel may be increased smoothly by making the wheel turn faster. Quantum angular momentum behaves differently. Its measurable values appear in units determined by a fundamental constant of nature. That natural unit is the reduced Planck constant. Max Planck first introduced the Planck constant while studying the radiation emitted by heated objects. The constant revealed that energy exchange at microscopic scales occurs in discrete quantities. The reduced Planck constant is derived from the Planck constant and appears throughout quantum mechanics, particularly in the mathematics of angular momentum. Its value is extraordinarily small on everyday scales, which helps explain why quantized angular momentum is not obvious in rotating bicycles, planets, or ceiling fans. At the scale of atoms and elementary particles, however, it becomes fundamental. The electron is described as a spin 1/2 particle. This phrase does not mean that the electron has half as much spin as some ordinary object, nor does it mean that it performs half a physical rotation. It identifies the mathematical category to which the electron belongs and determines the measurement results permitted by quantum theory. When the spin component of an electron is measured along any chosen axis, only two results are possible. The result may be positive 1/2 of reduced Planck constant or negative 1/2 of reduced Planck constant. These two outcomes are commonly called spin up and spin down. The labels are useful, provided they are not taken too literally. Spin up does not mean that the top half of an electron is rotating in one direction. Spin down does not mean that the same electron has reversed its mechanical rotation. The electron has no known surface, top, bottom, or internal axle. Up and down refer to the relationship between the quantum state and the direction selected by the measurement apparatus. A magnetic field may define the vertical axis of an experiment. Relative to that axis, one result is labelled spin up and the other spin down. The apparatus could instead be turned sideways. It would then measure the spin component along a horizontal axis, producing two outcomes defined relative to that new direction. The words up and down remain, although they may now refer to left and right from the laboratory's point of view. Quantum physicists are sometimes surprisingly relaxed about directional vocabulary. The measurement axis is therefore essential. Spin up is not an absolute condition existing independently of every possible direction. It means spin up relative to a specified axis. Quantum mechanics describes the electron using a spin state. This state contains everything the theory can predict about the outcomes of future spin measurements. It may describe an electron that will certainly produce spin up along one axis. It may instead describe a superposition in which measurements along that axis have different probabilities. The state is not merely a list of hidden classical directions waiting to be uncovered. Its structure determines how probabilities change when the measurement direction changes. An electron prepared as spin up vertically does not generally possess a definite horizontal spin result at the same time. Wolfgang Pauli developed mathematical operators that represent spin measurements along three mutually perpendicular directions. These are known as the Pauli spin matrices. One corresponds to a measurement along one spatial axis, another to a second axis at right angles to it, and the third to the remaining perpendicular direction. The Pauli matrices encode several unusual features of spin 1/2 systems. They produce the two permitted component values, describe how spin states change under rotations, and reveal why measurements along different axes cannot always be assigned simultaneous definite results. Although the matrices are compact, the physical message is broad. Choosing a measurement direction is not simply choosing which side of a pre-existing classical arrow to inspect. Different directions correspond to different quantum observables, and a state that is definite for one may be indefinite for another. There is also an important distinction between the total spin magnitude and a measured spin component. Every electron possesses the same fixed total spin magnitude. In the mathematical language of quantum mechanics, that magnitude is given by the square root of 3 divided by 2 times reduced Planck constant. A single component measured along a chosen axis has one of the two values, positive 1/2 or negative 1/2 of reduced Planck constant. The total magnitude is therefore not the same as either individual measurement result. This may feel unfamiliar because an ordinary arrow has definite components in all three directions at once. Knowing those components allows the arrow's complete length and orientation to be reconstructed. Quantum spin does not behave like a hidden classical arrow with 3 simultaneously fixed components. Yet spin remains a genuine form of angular momentum. It obeys the mathematical relationships associated with rotations. It contributes to the total angular momentum of atoms, particles, and larger systems. It can combine with orbital angular momentum. It can be transferred between matter and electromagnetic radiation. Most importantly, the total angular momentum of an isolated system remains conserved when spin changes are included. When an atom emits a photon, angular momentum may pass from the atom into the light. When a magnetic material changes its internal spin arrangement, the larger object can respond mechanically. In particle collisions, the spins of the incoming and outgoing particles help determine which processes are permitted. Spin therefore performs the physical work expected of angular momentum, even though it does not arise from classical rotation. Its reality is found not in a hidden spinning surface, but in measurable outcomes, magnetic interactions, conservation laws, rotational symmetry, and the precise mathematical structure of quantum theory. An electron does not need to turn like a wheel in order to possess angular momentum. It carries spin because the quantum state of an electron participates in nature's rules for rotation in a distinctive and unavoidable way. The Stern-Gerlach arrangement can be imagined as more than a device for discovering that spin has quantized outcomes. It can also be used to reveal something deeper. Measuring spin along one direction changes what can be predicted about measurements along another. Consider an idealized beam of spin 1/2 particles entering an uneven magnetic field. The field defines a particular measurement axis. If the magnets are arranged vertically, the apparatus measures the vertical component of spin. The incoming beam separates into 2 paths. One contains particles producing the result called spin-up along the vertical axis. The other contains particles producing spin down along that same axis. Suppose the lower path is blocked, and only the vertically spin-up particles are allowed to continue. The apparatus has now done 2 things. It has measured the particles, and it has prepared a new beam in a definite vertical spin state. If this prepared beam enters a second Stern-Gerlach apparatus, Also aligned vertically, every particle follows the spin-up path. None appears in the spin-down output. The repeated result is completely predictable. Once a particle has been prepared as spin-up along the vertical axis, an immediate measurement along that same axis returns spin-up with certainty. This reliability may sound pleasantly classical. A compass needle pointing north will still point north when inspected again a moment later, provided nothing disturbs it. The similarity does not last very long. Turn the second Stern-Gerlach apparatus so that it measures spin along a horizontal direction instead. The particles entering it are still spin up vertically. Yet the horizontally aligned device does not direct every particle into one output. The beam divides again. Roughly half the particles produce one horizontal result, while the other half produce the opposite result. A state that was perfectly definite relative to the vertical axis does not provide a definite result relative to the horizontal axis. This is not caused by small variations in the quality of the particles. It is not because some were secretly prepared a little more accurately than others. Even when every particle is prepared in the same vertical spin state, quantum mechanics predicts two possible horizontal results with equal probabilities. Now select one of those horizontal outputs. The particles leaving that path have been prepared in a definite horizontal spin state. Their previous vertical preparation has not vanished from history, but it no longer determines a certain answer to a new vertical measurement. Pass this horizontally prepared beam through a third Stern-Gerlach apparatus aligned vertically. Once again, two outputs appear. Some particles produce spin up vertically, while the rest produce spin down vertically. The certainty created by the first vertical preparation has been lost after the horizontal measurement. The sequence is striking. A vertical measurement produces a definite vertical result. Repeating that measurement preserves the result. Inserting a horizontal measurement between the two vertical devices restores uncertainty about the final vertical outcome. The horizontal apparatus has not merely uncovered information that was already sitting quietly inside the particle. It has prepared the particle in a state that is definite horizontally and indefinite vertically. Measurements of spin along different directions are therefore described as incompatible observables. An observable is a measurable physical property represented within quantum mechanics by a mathematical operator. The vertical spin component is one observable, the horizontal component is another. For compatible observables, quantum theory may allow a state in which both properties possess definite values at the same time. Incompatible observables do not generally permit this. A particle prepared with a definite spin component along one axis will usually lack a definite spin component along an axis pointing in a different direction. The mathematical expression of this relationship is that the corresponding operators do not commute. Non-commuting observables are ones for which the order of operations matters. Measuring vertical spin and then horizontal spin does not produce the same physical preparation as measuring horizontal spin and then vertical spin. The formal mathematics can be written compactly, but the physical meaning is already visible in the sequence of beams. Each apparatus changes the set of future outcomes that can be predicted with certainty. This disturbance should not be pictured as clumsy machinery, knocking a hidden microscopic magnet sideways. It is tempting to imagine that the electron begins with a definite little arrow, only for the magnetic field to jolt it out of position. That explanation would turn the experiment into a problem of imperfect equipment. Quantum mechanics says something more fundamental. The particle is not assigned three simultaneously definite spin components resembling the three components of an ordinary classical arrow. A classical arrow can possess a fixed amount pointing vertically, another amount pointing horizontally, and a third amount pointing through the remaining spatial direction. Those components may be unknown, but they can still be treated as existing together. A quantum spin state does not generally work that way. When vertical spin is definite, horizontal spin is represented by a spread of possible outcomes. When horizontal spin is made definite, the vertical result becomes uncertain. The uncertainty is not merely ignorance about a complete set of values that the particle has carried all along. This is why preparation and measurement are so closely linked. A measuring device reveals one of the values permitted for the chosen observable. At the same time, the system emerging from that measurement is left in a state associated with the result obtained. A particle found to be spin-up vertically leaves the apparatus prepared to produce spin-up in a repeated vertical test. A particle found to have one horizontal result is similarly prepared, relative to the horizontal axis. The apparatus is therefore not a passive window through which a complete collection of hidden properties is viewed. It helps define the physical question being asked and prepares the state relevant to future questions. None of this means that human awareness creates the result. The important interaction is physical. The particle becomes correlated with the measuring apparatus and its environment, allowing a definite recorded outcome to appear. A conscious observer may read the record later, perhaps after making tea, without changing the earlier beam separation. The lesson comes from the structure of the measurements themselves. If spin were simply an unknown classical direction hidden inside the particle, selecting particles that point vertically upward should reveal a stable geometric orientation. Measuring them horizontally might uncover the horizontal component of that same arrow, but it should not erase the previously definite vertical component. The actual sequence refuses this explanation. A measurement along one axis can create certainty along that direction, while removing certainty along another. What can be predicted depends not only on the particle's earlier history, but also on which observable has most recently been measured and prepared. Spin is therefore not a tiny arrow awaiting more careful inspection. It is a quantum property whose possible outcomes are tied to the direction of measurement and whose state changes through the act of physical measurement. The Stern-Gerlach apparatus does more than divide a beam. By turning the magnets and repeating the experiment, it reveals that quantum properties cannot always be collected into one complete classical picture. Some questions can be answered precisely, but answering one of them can change which other answers remain available. A quantum spin state does not always correspond to one definite outcome along the direction we happen to choose. It can instead exist as a superposition of the possible results. Quantum superposition allows a state to contain coherent contributions associated with more than one measurement outcome. The word coherent is important. It means that the different contributions retain a precise mathematical relationship with one another, allowing them to combine and interfere in ways that ordinary probabilities cannot. Consider an electron prepared with a definite spin result along a horizontal axis. If its spin is then measured horizontally again, the same result can be predicted with certainty. Relative to a vertical measurement, however, that horizontally prepared state is described as a superposition of spin up and spin down. This does not mean that half of the electron is spin up while the other half is spin down. It also does not mean that the electron rapidly switches between two hidden orientations whenever nobody is measuring it. Superposition is not a description of an object secretly jumping back and forth between ordinary classical states. Instead, both vertical possibilities contribute to the complete quantum state. When a vertical measurement is eventually performed, only one result is recorded. Across many identically prepared electrons, the two vertical outcomes appear with probabilities determined by the state. For a spin state prepared exactly horizontally, the probabilities of finding spin up or spin down vertically are equal. Roughly half of a large collection will produce one result, while the remainder will produce the other. The result for any individual electron cannot be predicted with certainty, even though the statistical pattern for many electrons can be calculated with great accuracy. Quantum mechanics represents the contributions to a superposition using probability amplitudes. These are not ordinary probabilities. A probability is obtained only after the magnitude of an amplitude has been processed according to the rules of the theory. Probability amplitudes can also carry a relative phase. Phase describes the mathematical relationship between the different contributions to a state. Two spin states may give identical probabilities when measured vertically, while behaving differently when measured along another direction, because their relative phases are different. This is one reason why a quantum state contains more information than a simple list of outcome probabilities. Knowing that vertical measurements are equally likely to produce spin up or spin down does not completely identify the state. The relative phase between those two contributions helps determine what will happen if the measurement apparatus is rotated. A useful way to organize all of these possibilities is the Bloch sphere, named after Felix Bloch. The Bloch sphere is a geometric representation of the pure quantum states available to an ideal spin 1/2 system. A pure state is one that contains the fullest possible information permitted by quantum mechanics, rather than representing uncertainty about which of several differently prepared states is present. Every point on the surface of the Bloch sphere corresponds to a possible pure spin state. An arrow is often drawn from the center of the sphere to the chosen point. This is called the Bloch vector. The arrow can be helpful, but it must be interpreted carefully. It is not the physical axis of an electron. It does not show a tiny ball pointing in a particular direction, and it certainly does not reveal which way an invisible surface is rotating. The Bloch vector represents the structure of the quantum state and the probabilities associated with different spin measurements. The north pole of the sphere can represent spin up along a chosen vertical axis. The south pole then represents spin down along that same axis. These are the two states that produce definite vertical outcomes. Points around the equator represent states that are equal superpositions of vertical spin up and vertical spin down. Different positions around the equator correspond to different relative phases between those contributions. One point might represent spin up along a horizontal axis. The point directly opposite would represent spin down along that horizontal direction. Two other points could represent the corresponding definite states along the remaining perpendicular axis. All of these states contain equal probabilities for vertical spin up and spin down. Their differences become visible only when measurements are made along other directions. The Bloch sphere therefore gathers a large amount of quantum information into a picture that feels almost classical, while remaining fundamentally different from a diagram of a physical object. The sphere is a map of state space, not a model of the electron shape. The state can also move across this abstract sphere. When a spin-carrying particle is placed in a magnetic field, its magnetic moment interacts with the field. The quantum state evolves in a way often described as spin precession. On the Bloch sphere, the state appears to rotate around the axis defined by the magnetic field. The rate of this motion is connected to the Larmor frequency, named after Joseph Larmor. The frequency depends on the strength of the magnetic field and on the relationship between the particle's magnetic moment and its angular momentum. There is a classical resemblance here. A spinning top placed in a gravitational field may wobble around the vertical direction instead of simply falling. A classical magnetic moment can also precess around an applied field. Quantum spin precession is not evidence that an electron is physically wobbling like a tiny top. What evolves is the quantum state and the relative phase between its components. The Bloch vector traces a path through state space because the probabilities of future measurements are changing with time. This evolution can be controlled with remarkable precision. A steady magnetic field establishes a preferred axis and causes the state to precess at its Larmor frequency. An additional oscillating electromagnetic field can then be applied for a carefully chosen duration. When its frequency matches the relevant energy separation, it can drive the spin state from one region of the Bloch sphere to another. A short pulse may move the state from the North Pole towards the equator. A longer pulse may carry it all the way to the South Pole, changing a state that produces spin up with certainty into one that produces spin down. By controlling the strength, timing, phase, and direction of these pulses, researchers can create superpositions, reverse spin states, and perform sequences of quantum operations. This is not merely an elegant theoretical exercise. Similar methods are used in nuclear magnetic resonance imaging, atomic clocks, quantum sensors, and experimental quantum computers. Each technology relies on the controlled evolution of quantum states carrying angular momentum. A spin-based quantum bit can be prepared at one pole of its Bloch sphere, placed into a superposition near the equator, allowed to evolve, and later measured. The success of the operation depends on preserving the delicate relative phase that makes the state coherent. Environmental interactions can disturb that phase through decoherence, gradually replacing a useful quantum superposition with behavior that resembles an ordinary statistical mixture. This is why controlling spin states requires careful isolation and exceptionally precise fields. Yet nothing in the process demands literal mechanical rotation. The magnetic fields do not grip a microscopic sphere and twist it around an axle. They alter the evolution of a quantum state according to the rules governing intrinsic angular momentum. Superposition shows why asking for the single direction of spin can be misleading. A state may be definite along one axis while containing several possible outcomes along another. It may occupy a point on the Bloch sphere that encodes both probabilities and relative phase, without corresponding to a hidden classical orientation. The electron does not need to decide between two ordinary directions before measurement. Its state can contain both possibilities coherently, and the relationship between them shapes everything that can later be observed. Spin has no tiny physical arrow buried inside the particle, but it has a precisely controllable direction in quantum state space, and that abstract direction can be manipulated with enough accuracy to build real technologies. Spin one-half particles are described using mathematical objects called spinors. A spinor is not a tiny arrow hidden inside a particle, nor is it a picture of an internal axis. It is a mathematical structure that represents how a quantum state responds when the surrounding coordinate system, magnetic field, or physical apparatus is rotated. The foundations of this idea appeared before physicists understood its importance for particles. Elie Joseph Cartan developed the mathematics of spinors during the early 20th century while studying geometry and transformations. At the time, spinors belonged largely to abstract mathematics. Their connection to electrons and other quantum particles emerged only later. Ordinary vectors respond to rotations in a familiar way. An arrow pointing upwards can be turned through 90 degrees until it points sideways. Continue rotating it, and after a complete turn of 360 degrees, the arrow returns to exactly the orientation with which it began. The same is true for many everyday objects. Rotate a book through one complete turn and, assuming the pages remain attached, it looks unchanged. Classical geometry treats the final orientation as identical to the starting one. Spinors behave differently. When the quantum state of a spin one-half particle is rotated through 360 degrees, the corresponding spinor does not return to its original mathematical form. Instead, the complete state acquires a minus sign. Written verbally, the transformation can be described as follows. The rotated spinor equals negative 1 times the original spinor. At first, this may seem like a distinction without a difference. Multiplying an entire isolated quantum state by -1 does not change the probabilities of its measurement outcomes. The magnitudes of its probability amplitudes remain the same, so measurements performed on that state alone cannot reveal whether the overall sign is positive or negative. An electron does not emerge visibly upside down after one complete rotation. It does not gain negative mass, reverse its electric charge, or begin behaving in a generally disagreeable manner. The sign matters when the rotated state can be compared with another state that was not rotated. Quantum mechanics allows amplitudes to interfere. If a particle's quantum state is divided into two coherent paths, one path can experience a spin rotation while the other remains unchanged. When the paths are brought together again, the relative sign between them affects the interference pattern. After a rotation of 360 degrees, The rotated contribution has the opposite sign from the unrotated contribution. The two paths may therefore reinforce or cancel differently from the way they would have before the rotation. The overall sign of one isolated state remains unobservable, but the relative sign between two coherent contributions produces measurable consequences. Continue the spinor rotation through another 360 degrees, giving a total turn of 720 degrees, and the original mathematical state returns. The first complete rotation introduces a negative sign. The second introduces another negative sign. Together, the two changes restore the spinor to its starting form. This does not mean that an electron must physically turn around twice before it looks normal again. The particle is not a microscopic object that becomes twisted after one revolution and untwisted after two. The unusual behavior belongs to the quantum state and to the geometry of the transformations acting upon it. The reason lies in the mathematical relationship between ordinary rotations and spinor rotations. The possible orientations of familiar objects are organized by what mathematicians call the three-dimensional rotation group. This structure describes how ordinary vectors and objects transform when rotated in space. Spin 1/2 states are governed by a closely related spin group. The spin group is said to provide a double covering of the ordinary rotation group. Conceptually, this means that two different spinor transformations correspond to each ordinary spatial orientation. A classical object can return to the same visible orientation after one complete turn, while the spinor retains information about which of two mathematically distinct routes through the transformation space has been taken. Only after a second complete turn does the spinor complete the full journey back to its original state. A useful comparison can be made with an object attached to its surroundings by flexible strands. Turning the object through one complete rotation may return its visible face to the starting direction, while leaving the strands twisted. A second rotation can remove the twist without requiring the object to reverse its path. This comparison captures something about the connected sequence of rotations, though it should not be mistaken for a mechanical model of the electron. No physical strings are attached to a particle. The analogy simply shows how an object can regain its ordinary orientation before the entire configuration has returned to its initial state. The phase change associated with spinor rotation has been tested experimentally. Neutrons are spin 1/2 particles, making them suitable for demonstrations using neutron interferometry. In these experiments, a coherent neutron beam is divided into separate paths. A magnetic field acts upon the neutron spin along one route, producing a controlled rotation, while the other route provides an unrotated reference. When the paths are recombined, the resulting interference depends on the relative phase between them. Experiments have observed the sign change associated with a 360-degree spin rotation, and the return to the original phase after 720 degrees. Related methods involving electrons, atoms, and other quantum systems reveal the same underlying transformation rules. These results are not philosophical decorations added to quantum mechanics. They are measurable consequences of the way spin 1/2 states respond to rotations. The strange 720-degree behavior therefore provides an especially clear warning against the tiny spinning ball. A classical sphere returns completely to its initial configuration after one ordinary rotation. A spinor does not. Its transformation follows a deeper geometry in which the familiar rotations of physical space correspond to only part of the journey through quantum state space. Spin belongs to this geometry. It describes how a particle's quantum state transforms under rotations, including changes of phase that become visible through interference. The electron does not need to rotate twice around a hidden axle. Nothing inside it is physically turning through 720 degrees. Instead, its spinor carries a structure that ordinary arrows do not possess. One full rotation restores the apparent spatial orientation, but changes the quantum phase. Two full rotations restore the complete state. This curious result is not a flaw in the name spin. It is evidence that quantum angular momentum belongs to a richer mathematical world than the turning wheels, planets, and spinning tops that first inspired the comparison. The early theory of electron spin had identified something real, but it had not yet explained why that property existed. Spin had been added to quantum mechanics because experiments demanded it. Physicists still wanted a deeper theory in which spin appeared naturally. Paul Adrian, Maurice Dirac took up that challenge during the late 1920s. Quantum mechanics had transformed the study of atoms, while Albert Einstein's special theory of relativity had transformed the understanding of space, time, energy, and motion. Both theories were successful, but bringing them together was not straightforward. Erwin Schrödinger's wave equation described many slowly moving quantum systems with remarkable accuracy. It explained atomic energy levels and wave behavior, yet it had not been constructed as a fully relativistic description of an electron moving near the speed of light. Special relativity requires space and time to be treated as parts of one structure. Energy and momentum must also obey a precise relativistic relationship. Simply inserting that relationship into ordinary quantum mechanics created mathematical difficulties, including problems with probability. Dirac searched for an equation that was relativistic from the beginning while preserving the probabilistic meaning of quantum theory. He wanted it to describe how an electron state changes through space and time without abandoning the successful foundations of quantum mechanics. The result, published in 1928, became known as the Dirac equation. The equation did not begin by imagining an electron as a tiny spinning sphere and then attaching an extra correction. Instead, it required a quantum state with several components and naturally described a particle with spin 1/2. Spin emerged from the mathematical structure needed to make quantum mechanics compatible with special relativity. It was no longer merely an additional rule introduced to repair atomic spectra. It belonged to the relativistic description of the electron itself. The Dirac equation also clarified the electron's magnetic behavior. A charged particle with orbital angular momentum has a particular relationship between magnetism and angular momentum. The electron's intrinsic magnetic moment was approximately twice that simple orbital expectation. Earlier models had struggled with this factor of 2. In Dirac's theory, it appeared naturally. The equation predicted an electron magnetic factor of 2, connecting spin 1/2, electric charge, and relativistic quantum mechanics within one framework. The theory also contained solutions corresponding to negative energies. At first, these seemed troubling. If ordinary electrons could continually fall into lower negative energy states, stable matter would be difficult to explain. Dirac eventually concluded that the theory implied a new particle with the same mass and spin as the electron but the opposite electric charge. This was the positron, the electron's antiparticle. In 1932, Carl David Anderson observed cosmic ray tracks in a cloud chamber. One track curved through a magnetic field, as though it belonged to a particle with the electron's mass but a positive charge. Its changing curvature after passing through a lead plate helped establish its direction of motion. The positron showed that the strange additional solutions of the Dirac equation corresponded to a real part of nature. A theory developed to unite relativity and quantum mechanics had explained spin more deeply and predicted antimatter. The modern picture became richer through quantum electrodynamics, the quantum field theory describing electrically charged particles and their interactions with the electromagnetic field. In this framework, an electron is an excitation of the electron field. Its measurable magnetic properties are influenced by interactions with the quantum electromagnetic field. The basic Dirac prediction gives a magnetic factor of 2. Experiments reveal a value slightly larger than 2. This small difference is called the anomalous magnetic moment of the electron. Julian Schwinger calculated the first quantum correction in 1948. The correction arises because the electron cannot be treated as completely isolated from the quantum electromagnetic field. Its interactions modify the measured relationship between spin and magnetic moment. This is sometimes described using virtual particles. The language is useful when handled carefully, but the calculation concerns quantum fields and permitted interactions rather than tiny hidden objects briefly appearing in an ordinary mechanical sense. Later calculations included increasingly subtle contributions from quantum electrodynamics and from other known particles. Experimental methods also became extraordinarily precise. The electron's magnetic properties have been measured to roughly parts in a trillion, and theoretical calculations agree at a similarly remarkable level. The comparison is among the most precise tests ever performed in physics. That precision matters because even a tiny disagreement could point towards unknown particles or interactions. So far, the electron's magnetic behavior has remained in exceptional agreement with established quantum theory. Dirac's achievement changed the meaning of spin. Spin 1/2 was not evidence of a concealed rotating surface beneath the electron's charge. It was a consequence of how the electron's quantum field transforms under quantum mechanics, special relativity, and space-time symmetry. The electron carries angular momentum and a magnetic moment, but it does not need internal pieces circling an axis. Its spin is written into the relativistic structure of the theory. What once looked like a peculiar extra property attached to the electron became part of a deeper description linking matter, magnetism, antimatter, and the geometry of space-time. Inside an atom, electron spin does not exist in isolation. It becomes part of a larger pattern of angular momentum that helps determine the atom's energy levels, its spectral lines, and the ways it can interact with light. The first important distinction is between intrinsic spin and orbital angular momentum. Electron spin belongs to the electron itself. Every electron carries the same fixed amount of intrinsic spin, regardless of the atomic state it occupies. Orbital angular momentum is different. It arises from the spatial form of the electron's quantum state around the atomic nucleus. The word orbital can be slightly misleading because an atomic orbital is not a precise path resembling the orbit of a planet. It is a quantum state described by a wave function, with a characteristic distribution through space. Some orbitals possess no orbital angular momentum, while others carry increasing permitted amounts. An electron inside an atom can therefore possess intrinsic spin and orbital angular momentum at the same time. Quantum mechanics combines these contributions to produce the electron's total angular momentum. This process is known as angular momentum coupling. In classical physics, two angular momenta might be pictured as arrows. The arrows can be placed together, and their combined direction and length can be found by ordinary geometry. Quantum angular momentum does not behave quite so freely. The individual angular momenta have quantized magnitudes, and their combination permits only particular total values. If orbital angular momentum and spin are coupled, the total electronic angular momentum is restricted by quantum rules, rather than allowed to take every intermediate magnitude. For an electron whose spin is 1/2, a given non-zero orbital angular momentum generally combines with spin to produce two possible total angular momentum values. These correspond loosely to spin contributing either with or against the orbital angular momentum, although neither contribution should be imagined as a permanently fixed classical arrow. The interaction connecting them is called spin-orbit coupling. An electron moving within the electric field of an atomic nucleus experiences electromagnetic effects that depend on its orbital state. In the electron's frame of reference, these effects can be described partly as an effective magnetic field. The electron's intrinsic magnetic moment interacts with that field, shifting the energy of the atomic state. A complete description must also include special relativity and Thomas precession. The result is not simply the attraction or repulsion of two tiny bar magnets. Spin-orbit coupling is a relativistic quantum interaction, involving the electron's motion, its intrinsic magnetic moment, and the electric field created by the nucleus. The energy shift depends on how orbital angular momentum and spin combine into total angular momentum. States that would otherwise possess the same energy may therefore separate into nearby levels. These small divisions contribute to atomic fine structure. The word fine reflects the scale of the effect. The main spectral structure comes from the larger energy differences between atomic states. Fine structure divides some of those levels into more closely spaced components, producing additional detail in the spectrum. Hydrogen provides the simplest major example, because it contains one proton and one electron. The broad energy pattern can be understood through the electron's quantum states in the electric field of the proton. More accurate observations reveal smaller separations requiring relativistic corrections. In a fully relativistic treatment using the Dirac equation, electron spin and spin orbit behavior appear naturally. The hydrogen fine structure also includes other relativistic contributions, so spin-orbit coupling should not be treated as the only cause. Together, these effects refine the predicted energy levels and bring theory into closer agreement with observation. In heavier atoms, the situation becomes more complicated. Many electrons interact with the nucleus and with one another. Their orbital angular momenta and spins can combine in several ways, producing dense collections of energy levels. Spin-orbit effects also tend to become stronger in atoms with larger nuclear charge. A heavier nucleus creates a more intense electric field, especially near the center of the atom. Inner electrons may move at substantial fractions of the speed of light, making relativistic effects increasingly important. This is one reason heavy elements can display particularly strong fine structure. Spin-orbit coupling influences their spectra, their chemical behavior, and even visible properties such as the color of certain materials. Gold provides a familiar example of the wider importance of relativistic atomic effects. Its distinctive color cannot be explained accurately using a purely non-relativistic treatment. Mercury's unusual liquid state at ordinary temperatures is also connected partly to relativistic changes in electron behavior. Spin-orbit coupling belongs to this broader, relativistic reshaping of heavy atoms, although it is not solely responsible for every such effect. Atomic states are organized using several quantum numbers. The principal quantum number describes the main energy shell and is closely connected to the overall scale of the electron spatial state. The orbital angular momentum quantum number identifies the permitted amount of orbital angular momentum and helps determine the shape of the orbital. A spin quantum number identifies the electron as a spin 1/2 particle. The total angular momentum quantum number describes the permitted result of combining orbital angular momentum with intrinsic spin. Additional magnetic quantum numbers describe allowed components of angular momentum along a selected axis. These labels provide a systematic way to distinguish atomic states that may otherwise appear similar. The same angular momentum structure controls how atoms absorb and emit light. When an electron makes a transition between two atomic energy states, the atom must conserve energy and angular momentum. The emitted or absorbed photon carries energy, momentum, and angular momentum of its own. Not every imaginable transition is therefore equally possible. Selection rules describe which transitions are allowed, strongly favoured, weakly permitted or forbidden under particular interactions. For common electric dipole transitions, the orbital angular momentum changes according to a specific quantum rule, while the total angular momentum must also change within defined limits. A transition between two states, both having zero total angular momentum, is not allowed through the ordinary electric dipole process. The word forbidden does not always mean absolutely impossible. Some transitions can occur through weaker magnetic or higher order electromagnetic processes. They may simply happen far more slowly than strongly allowed transitions. These rules shape the spectral fingerprints of the elements. When atoms in a laboratory gas are excited, their permitted transitions produce sharply defined wavelengths. The same principles apply in stellar atmospheres, glowing nebulae, interstellar clouds, and distant galaxies. Astronomers can identify hydrogen, helium, oxygen, iron, calcium, and many other elements by matching observed spectral lines to known atomic transitions. Fine structure and spin-dependent effects add detail to these patterns, allowing researchers to investigate temperature, density, magnetic fields, motion, and chemical composition across enormous distances. The National Institute of Standards and Technology maintains extensive collections of atomic data, including measured energy levels, transition wavelengths, spectral classifications, and angular momentum assignments. These reference tables allow laboratory physicists and astronomers to compare observations with carefully established atomic measurements. A tiny separation between spectral lines may encode the combined influence of orbital angular momentum, intrinsic spin, relativity, and electromagnetic interaction. None of this requires an electron to rotate around an internal surface. Spin reshapes the atom because it combines with orbital angular momentum according to precise quantum rules. It shifts energy levels, alters permitted transitions, and leaves measurable patterns in the light reaching us from laboratories and from the distant universe. The electron is not spinning like a miniature planet, yet its intrinsic angular momentum is written clearly across the spectrum of almost every atom. The influence of spin extends far beyond the behavior of an individual electron. When many identical particles are brought together, their intrinsic spin helps determine how the entire collection is allowed to organize itself. This connection begins with Wolfgang Pauli's exclusion principle. The exclusion principle states that no two identical fermions can occupy exactly the same quantum state at the same time. Electrons are fermions, but they are not the only examples. Protons, neutrons, and quarks also belong to this broad family of particles. All of them possess half-integer spin. Electrons, protons, and neutrons have spin 1/2, while other fermions can carry larger half-integer values. Their shared behavior is not an accidental resemblance. It is tied directly to the mathematical relationship between intrinsic spin and particle statistics. Enrico Fermi and Paul-Adrien Maurice Dirac developed the statistical framework now called Fermi-Dirac statistics. It describes how large collections of identical fermions distribute themselves among the quantum states available to them. The word statistics here does not mean that the particles are behaving randomly without rules. It refers to the precise way their collective quantum state is constructed, and to the restrictions this places upon how they may share energy levels. Inside an atom, 2 electrons can occupy the same spatial orbital, but only if their complete quantum states remain different. The distinction is commonly expressed through their spin measurements along a chosen axis. One electron may be described as spin up along that axis, while the other is spin down. This does not mean that 2 tiny arrows sit inside the orbital, permanently pointing in opposite directions. The electrons occupy a combined quantum state, with the symmetry required for identical fermions. Their spin relationship helps keep their total states distinct, even when the spatial part of each electron's state is the same. The deeper connection is expressed by the spin statistics theorem. Relativistic quantum field theory links particles with half-integer spin to fermionic behavior. Particles with integer spin follow bosonic behavior instead. Bosons include particles such as photons, whose collective rules allow many identical particles to occupy the same quantum state. Fermions behave differently because their joint quantum state changes sign when 2 identical particles are exchanged. Suppose 2 identical electrons are described together. If every label associated with the first electron is swapped with the corresponding label of the second, the complete quantum state gains a negative sign. The particles themselves are indistinguishable, so there is no physical tag revealing which electron was originally called the first. Yet the antisymmetric structure of the state has an important consequence. If both electrons were placed in exactly the same complete quantum state, exchanging them would change nothing. The state would have to remain identical because the 2 descriptions would be indistinguishable. Fermionic antisymmetry, however, requires the exchange to multiply the state by -1. The only state that can equal its own negative without contradiction is a state with zero amplitude. In physical terms, that arrangement simply cannot occur. This is the mathematical origin of exclusion. The result shapes the entire architecture of atoms. Electrons fill available states in a structured order rather than all gathering into the lowest energy state. Once a state is occupied, another identical electron must differ in at least one quantum property. The first atomic shell can hold only a small number of electrons. Higher shells contain additional orbitals, each with their own energy and angular momentum structure. As the nuclear charge increases from one element to the next, electrons gradually fill these states. This layered arrangement creates the repeating pattern of the periodic table. Elements in the same column often display similar chemical behavior because they possess related arrangements of outer electrons. These valence electrons are the ones most directly involved in chemical bonding, electrical conduction, and reactions with other atoms. Hydrogen has one outer electron and tends to form bonds that complete a more stable arrangement. Helium has a filled first shell and is chemically reluctant to react. Alkali metals possess a single outer electron that can be removed relatively easily, while noble gases generally have completed outer shells and are far less eager to participate. The variety of chemistry therefore depends partly on a rule rooted in spin. The exclusion principle also contributes to the size and stability of ordinary matter. Without it, all electrons in an atom could, in principle, descend into the same lowest energy state. Atoms would lose their familiar shell structure, and the periodic table would no longer possess its observed form. Instead, electrons are forced into a range of distinct quantum states. Some occupy states with higher energy and greater spatial extent. This gives atoms their layered dimensions and allows matter to form stable structures. Electrical repulsion between electrons is also important, as is the attraction between electrons and atomic nuclei. The solidity of matter cannot be credited to exclusion alone. Yet exclusion is essential to preventing enormous collections of electrons from occupying one identical state. The same principle becomes especially dramatic inside dense stars. A white dwarf is the compact remnant left after a star similar in mass to the Sun has exhausted its central nuclear fuel and expelled much of its outer material. Gravity compresses the remaining matter until the electrons are packed into an extremely dense collection. As compression increases, the exclusion principle forces electrons to occupy a wider range of momentum states. This produces electron degeneracy pressure, a quantum resistance to further compression that does not depend on ordinary thermal heat. A white dwarf can pack a mass comparable to that of the Sun into a body roughly the size of Earth. A spoonful of its material would have a mass of many tons under terrestrial conditions. Subramanian Chandrasekhar showed that electron degeneracy pressure cannot support an arbitrarily massive cold, non-rotating white dwarf. The limiting mass is approximately 1.4 times the mass of the Sun, although its exact value depends on composition and other physical details. Above that Chandrasekhar limit, further collapse or transformation becomes unavoidable. Neutron stars are denser still. Under extreme pressure, electrons and protons can combine through weak interactions to form neutrons. The remaining object may contain more mass than the Sun within a sphere only a few tens of kilometers across. Neutron degeneracy contributes to resisting gravity, but it is not the whole explanation. Strong nuclear interactions between particles become crucial at such extraordinary densities. The structure and maximum mass of a neutron star depend on the still uncertain equation of state of ultra-dense matter. Even here, however, the fermionic nature of neutrons remains fundamental. From the spacing of electrons in a simple atom to the support of a collapsed stellar remnant, the same relationship continues to operate. Half-integer spin determines fermionic statistics. Fermionic statistics produce exclusion. Exclusion shapes the possible arrangements of matter. Much of the solidity, stability, and chemical diversity surrounding us emerges from this quiet mathematical rule. Matter does not possess its structure because electrons are tiny spinning balls that refuse to touch. It possesses structure because intrinsic spin places electrons within the fermion family, and identical fermions cannot all settle into one indistinguishable quantum state. An individual electron carries an intrinsic magnetic moment associated with its spin. This allows the electron to respond to magnetic fields and in some respects to behave like a tiny quantum magnet. That comparison is useful, but it must remain carefully limited. The electron is not a miniature bar magnet with a physical north pole and south pole painted onto its surface. Its magnetic moment arises from intrinsic quantum properties rather than from a little charged sphere rotating mechanically. The magnetism of an actual material is more complicated still. A piece of iron contains an enormous number of electrons, and its behavior cannot be understood by considering each spin entirely on its own. The important physics comes from collective quantum states, interactions between neighbouring atoms, electron motion through the crystal, and the detailed arrangement of the material. Different combinations of these effects produce several distinct kinds of magnetism. Diamagnetism occurs when an applied magnetic field slightly alters the motion of electrons within a material, creating a weak magnetic response that opposes the applied field. This behaviour is present in all matter, although it is often hidden by stronger forms of magnetism. Materials such as bismuth display diamagnetism clearly and are weakly repelled from regions of stronger magnetic field. Paramagnetism appears in substances containing atoms or ions with unpaired electrons. Their magnetic moments tend to point in many directions when no external field is present. Applying a magnetic field makes a slight alignment more likely, producing a weak attraction towards the field. Thermal motion continually disrupts this ordering, so the effect generally fades when the field is removed. Ferromagnetism is the familiar behaviour associated with iron, cobalt, nickel, and permanent magnets. In a ferromagnetic material, interactions can favour neighbouring magnetic moments developing parallel correlations. Large numbers of moments then contribute to a shared magnetic order. The central interaction behind much of this behaviour is the quantum exchange interaction, studied by Werner Heisenberg during the development of quantum mechanics. Exchange is not simply the ordinary magnetic attraction between countless miniature bar magnets. Direct magnetic forces between electron moments are usually too weak to explain the strength of ferromagnetism by themselves. Instead, exchange arises from the combined effects of electric repulsion, the overlap of electron wave functions, the Pauli exclusion principle, and the requirement that the total quantum state of identical electrons possess the correct symmetry. Depending on the atoms, their spacing, and the structure of the material, exchange can favour different relationships. In some systems, nearby spin moments tend to align in the same general direction. In others, they favour opposing arrangements. Antiferromagnetism occurs when neighbouring magnetic moments tend to align in opposite directions. If the opposing contributions are equal, the material may have little or no overall magnetic moment, even though it contains strong internal magnetic order. Louis-Eugène Félix Néel made foundational contributions to the understanding of antiferromagnetism. He also helped explain ferromagnetism, in which neighbouring groups of magnetic moments oppose one another, but do not cancel completely. Ferromagnetic materials therefore retain a net magnetization. Magnetite provides a familiar example. Its different magnetic substructures point in opposing directions, yet one contribution is stronger than the other, leaving an overall magnetic effect. Even a ferromagnetic object is not necessarily one perfectly aligned block. Pierre Weiss introduced the concept of magnetic domains. A domain is a region within a material where large numbers of atomic magnetic moments share a common alignment. Different domains may point in different directions, causing their contributions to cancel across the object as a whole. An unmagnetized piece of iron can therefore contain strongly ordered regions without producing a large external magnetic field. When an external magnetic field is applied, domains already aligned favorably with the field can grow. Domain boundaries shift, while some regions change orientation. If enough of this organization remains after the external field is removed, the material becomes a permanent magnet. The process depends upon defects, crystal boundaries, temperature, and the ease with which domains can rearrange. A good permanent magnet must resist losing its ordered state, while a soft magnetic material may be designed to change magnetization readily. Magnetic order can also support travelling disturbances. Imagine a line of correlated magnetic moments in which one is tilted slightly away from its preferred direction. Its interaction with neighbouring moments can spread the disturbance through the material. This collective motion is called a spin wave. A spin wave does not involve individual electrons flying through the crystal in a wave-shaped path. It is a coordinated variation in magnetic order, passing from one region to another. In quantum theory, the energy of these collective disturbances appears in discrete excitations called magnons. Magnons are quasi-particles, meaning they describe organised behaviour within a material rather than existing as elementary particles in empty space. Researchers use magnons to study heat flow, magnetic dynamics, and possible methods of carrying information with less movement of electric charge. Some magnetic materials refuse to settle into even the usual ordered patterns. In a quantum spin liquid, magnetic moments remain strongly correlated while avoiding conventional ferromagnetic or antiferromagnetic order, even at very low temperatures. The name does not mean that literal spins flow around like water. It describes a highly entangled and continually fluctuating quantum state, in which no simple fixed arrangement dominates. Quantum spin liquids are difficult to identify experimentally, but they are important because they may support unusual collective excitations and reveal new forms of quantum matter. Everyday magnets are therefore not created by spin alone. Their behaviour emerges from intrinsic magnetic moments, orbital electron motion, exchange interactions, the Pauli exclusion principle, atomic arrangement, crystal structure, temperature, and the collective organisation of vast numbers of particles. A refrigerator magnet may appear simple and reassuringly ordinary. Beneath that familiar surface, however, its strength depends upon a coordinated quantum structure extending across countless atoms. The electrons are not tiny balls spinning together in neat mechanical formation. Their intrinsic spin helps create magnetic moments, while quantum interactions determine how those moments behave as a group. When enough of them become organised, a property that exists at the scale of individual particles becomes a force we can feel in the palm of a hand. Electron spin is only one example of intrinsic angular momentum. Entire atomic nuclei can also possess spin, created by the combined quantum states of the protons and neutrons they contain. Each proton and neutron is itself a spin 1/2 particle. Within a nucleus, their intrinsic spins combine with any orbital angular momentum associated with their quantum motion. The resulting nuclear spin belongs to the nucleus as a whole. Not every isotope has non-zero nuclear spin. Protons and neutrons often pair in ways that cancel their angular momentum contributions. A nucleus containing even numbers of both particles commonly has total spin 0, although the detailed rules depend on its internal quantum structure. Carbon-12, for example, contains 6 protons and 6 neutrons and has nuclear spin 0. Carbon-13 contains 1 additional neutron and has spin 1/2. The chemical element remains carbon, but the different isotope has a different nuclear spin and therefore behaves differently in magnetic resonance experiments. A nucleus with non-zero spin can possess a magnetic moment. When placed inside an external magnetic field, it may occupy several permitted energy states according to the measured component of its angular momentum along the field direction. For a spin 1/2 nucleus, there are 2 such possibilities. One has slightly lower energy than the other. The separation is extremely small compared with ordinary chemical or electronic energy differences, but it can still be measured with great precision. Isidor Isaac Rabi helped transform this subtle quantum effect into an experimental method. During the 1930s, Rabi and his colleagues developed molecular beam magnetic resonance. A beam of atoms or molecules passed through magnetic fields that separated or selected particular quantum states. Radio frequency electromagnetic energy was then applied. when its frequency matched the energy difference between permitted nuclear spin states, transitions occurred. This matching condition is called resonance. A system responds particularly strongly when the applied frequency corresponds to one of its natural energy separations. It is loosely comparable to pushing a swing at the correct rhythm, although the nucleus is not physically swinging or rotating. The comparison concerns efficient energy transfer rather than mechanical motion. Rabi's method allowed nuclear magnetic moments to be measured with exceptional accuracy and established the central principles of magnetic resonance. During the 1940s, Felix Bloch and Edward Mills Purcell independently extended the idea to large collections of nuclei in ordinary matter. Their work established nuclear magnetic resonance in bulk samples. Rather than sending separate atoms through a beam apparatus, researchers could place a liquid or solid inside a magnetic field and study the collective response of enormous numbers of nuclei. In thermal equilibrium, slightly more of the relevant nuclear spins occupy the lower energy state than the higher one. The difference is small, but a sample may contain so many nuclei that their combined magnetic response becomes detectable. An applied radio frequency field can disturb this equilibrium and create a coherent response. When the field is removed, the nuclear spin system gradually returns towards its original thermal condition. This return is known as relaxation. Different relaxation processes describe how the collective magnetization recovers along the main magnetic field and how coherence between spins fades across the sample. As the system evolves, it produces changing electromagnetic signals that can be detected by surrounding coils. The timing and strength of those signals reveal information about the nuclei and their surroundings. Nuclear magnetic resonance became an especially powerful tool in chemistry, because a nucleus does not resonate at exactly the same frequency in every molecule. Electrons surrounding the nucleus slightly shield it from the external magnetic field. The amount of shielding depends on chemical bonding, molecular geometry, nearby atoms, and the distribution of electric charge. These small frequency differences are known as chemical shifts. They allow researchers to distinguish nuclei occupying different chemical environments, even when those nuclei belong to the same element. Interactions between neighbouring nuclear spins can add further structure through spin-spin coupling. The resulting patterns help reveal which atoms are connected and how different parts of a molecule are arranged. A nuclear magnetic resonance spectrum can therefore act as a detailed molecular fingerprint. Chemists use it to identify unknown substances, confirm newly synthesized compounds, study molecular motion, examine proteins, and investigate the structures of complex biological molecules. Richard Robert Ernst greatly improved the technique through Fourier transform nuclear magnetic resonance. Earlier methods often examined frequencies gradually, which could be slow. Ernst helped develop pulse techniques in which a short burst of radio frequency energy excites a broad range of resonances at once. The sample then produces a complex signal containing contributions from many frequencies. A mathematical procedure called a Fourier transform separates this changing signal into its individual frequency components. The method made measurements faster, more sensitive, and far richer in information. Complicated sequences of carefully controlled pulses later allowed researchers to explore relationships between nuclei across several dimensions of spectral data. Magnetic resonance also became a method for looking inside the human body. Paul Christian Lauterbur showed that magnetic field gradients could make resonance frequency depend on position. A gradient creates a field that changes slightly from one location to another. Nuclei in different regions therefore respond at distinguishable frequencies. Peter Mansfield developed rapid and precise mathematical methods for encoding and reconstructing this spatial information. Together, these advances allowed nuclear resonance signals to be converted into detailed images. The medical technique is commonly called magnetic resonance imaging. The word nuclear is usually omitted, largely because it might sound rather less soothing to a patient entering a large humming scanner. Most clinical magnetic resonance imaging focuses on hydrogen nuclei. A hydrogen nucleus usually consists of a single proton and has spin 1/2. Hydrogen is abundant in the human body because it is present in water, fat, and many biological molecules. Strong magnetic fields, radio frequency pulses, and field gradients manipulate and locate the collective responses of these hydrogen nuclei. Differences in hydrogen density and relaxation behavior help distinguish muscle, fat, fluid, organs, and many forms of diseased tissue. Magnetic resonance imaging does not use ionizing radiation. Unlike medical imaging based on X-rays, it does not produce images by sending sufficiently energetic photons through the body to ionize atoms. The magnetic fields and radio waves are not causing the hydrogen nuclei to rotate as rigid balls. Nor are millions of microscopic protons physically turning in formation like unusually disciplined dancers. The instruments prepare, change, and measure quantum spin states and their associated magnetic moments. From identifying the structure of a molecule to producing an image of the brain, magnetic resonance depends on the same underlying fact. A nucleus can possess angular momentum without containing a little mechanical rotor. Its spin is quantum mechanical, but the signals it produces are practical, measurable, and precise enough to reveal both the architecture of matter and the hidden interior of the human body. Quantum spin becomes even more unusual when two particles share a state that cannot be divided cleanly into separate descriptions. This condition is known as spin entanglement. In an entangled state, the measurement statistics of one particle are connected to those of another. The pair must be described as a single quantum system, even when the particles later travel far apart. It is not enough to assign each particle its own independent spin state and then combine the two descriptions afterwards. A particularly important example is the spin singlet state, formed by two spin 1/2 particles. The pair has 0 total spin. If both particles are measured along the same chosen axis, the results are always opposite. When one particle produces spin up, the other produces spin down. If the first produces spin down, the second produces spin up. This remains true whether the apparatus is aligned vertically, horizontally, or along some other shared direction. The singlet state does not say in advance which particle will produce which result. Each individual outcome is unpredictable. What quantum mechanics predicts with certainty is the relationship between them. It may be tempting to assume that each particle carries a hidden instruction sheet. Perhaps one contains a complete list of answers for every possible measurement direction, while the other carries the opposite list. The measurements would then reveal values that had been quietly stored inside the particles from the beginning. Entanglement does not behave like that. Quantum theory does not require either particle to possess a definite spin result for every direction before the measurement occurs. Instead, the pair possesses a joint state whose correlations depend on the axes selected by the experimenters. David Joseph Bohm helped make this issue especially clear. He reformulated the earlier argument developed by Albert Einstein, Boris Podolsky, and Nathan Rosen using spin measurements rather than the more complicated position and momentum arrangement in the original proposal. In Bohm's version, a source produces two spin 1/2 particles in a singlet state and sends them in opposite directions. Each side contains an apparatus that can measure spin along one of several possible axes. The simplicity of two possible outcomes made the conflict between quantum mechanics and classical expectations easier to express experimentally. Albert Einstein had objected to the idea that quantum mechanics provided a complete description of physical reality. He hoped that the apparent randomness might reflect missing information carried by hidden variables. In a local hidden variable theory, the result on each side would be determined by information already present near that particle, without any physical influence travelling faster than light from the distant measurement. John Stuart Bell discovered a way to test broad classes of these explanations. Bell derived inequalities that limit how strongly the results from the two sides can be correlated if two assumptions are maintained together. The first is locality, meaning that a choice made at one distant apparatus cannot immediately affect the physical result at the other. The second is that the outcomes are determined by pre-existing local properties, even when those properties remain hidden from the experimenters. Quantum mechanics predicts that carefully chosen measurement directions can produce correlations stronger than those limits allow. The predicted pattern does not simply say that the particles usually disagree. If the two apparatuses are aligned in the same direction, the singlet results are perfectly opposite. As the relative angle between the measurement axes changes, the strength of the correlation changes in a smooth and precisely calculable way. For certain combinations of directions, those correlations violate a Bell inequality. This does not provide a method for sending a message faster than light. Each observer sees a locally random sequence of spin results. One side cannot choose whether the next outcome will be spin up or spin down, so no controllable signal can be encoded into the pattern. The correlation becomes visible only when the two sets of records are later brought together and compared through ordinary communication, which remains limited by the speed of light. John Francis Clauser carried out one of the first influential experimental tests of a Bell inequality during the 1970s. Later, Alain Speck and his colleagues performed more refined experiments in which measurement settings were changed while the particles were already travelling. Anton Zeilinger and many other researchers extended these methods further, improving the separation of the measuring stations, the efficiency of detection, and the control of possible experimental loopholes. Many celebrated Bell experiments use photon polarization rather than the intrinsic spin of massive particles. A photon does not behave exactly like an electron, but polarization measurements can produce two alternative outcomes, governed by closely related quantum mathematics. Other experiments have used electrons, atoms, ions, and defects in solid materials. Across these different systems, the central result remains consistent with quantum predictions. Experiments violate Bell inequalities. The meaning should be stated carefully. The violations do not prove that simple, usable messages race instantaneously between distant particles, nor do they identify one universally accepted mechanism operating beneath the mathematics. They rule out broad classes of theories in which all measurement results are fixed in advance by local hidden variables. Any deeper explanation reproducing the observed correlations must abandon at least part of that classical combination of locality and predetermined outcomes. Entanglement therefore shows that spin is more than an isolated label attached separately to each particle. Two particles can possess a definite total spin even when neither has its own definite result along every possible axis. The most complete description belongs to the relationship between them. This is a deeply non-classical feature. Two ordinary spinning objects could carry hidden orientations whether or not anyone measured them. An entangled spin pair cannot generally be understood as two tiny arrows with a matching set of concealed directions. The correlations have also become practical resources. Quantum communication protocols can use entangled states to reveal interception or establish correlations between distant users. Quantum information experiments use entangled spins to test operations, transfer states, and study the foundations of computation. Quantum sensors can exploit entanglement to improve sensitivity beyond what independent particles may provide. Researchers have also entangled electron spins, nuclear spins, trapped ions, neutral atoms, and solid-state quantum systems as potential building blocks for larger quantum devices. Spin entanglement begins with two particles and a simple pair of outcomes, but it reaches directly into the limits of classical explanation. Nothing needs to be literally spinning. Nothing carries a complete hidden compass for every possible question. The strange feature lies in the joint quantum state, where the particles possess relationships more definite than the separate properties we try to assign to each of them. Spin does more than influence how particles behave in magnetic fields. It helps determine what kind of particle each one is. The main framework used to organize known elementary particles is the Standard Model of Particle Physics. It describes the fundamental matter particles and 3 of the 4 known fundamental interactions: electromagnetism, the strong nuclear interaction, and the weak nuclear interaction. Gravity is not included in the Standard Model. It is described separately by Albert Einstein's general theory of relativity, and a complete quantum description of gravity remains one of the major unfinished problems in physics. Within the Standard Model, particles are not classified simply by their masses and electric charges. Each elementary particle is associated with a quantum field, and that field transforms in a particular way when space and time are rotated, shifted, or viewed from a different inertial frame. Intrinsic spin is part of this transformation behavior. A particle's spin therefore identifies the mathematical representation of space-time symmetry to which its field belongs. This may sound abstract, but the consequences are concrete. Spin helps determine which statistical rules the particle follows, which interactions are possible, how it can decay, and how it contributes to the total angular momentum of a physical process. The basic matter particles of the Standard Model are quarks and leptons. All of them are spin 1/2 fermions. The leptons include the electron, the muon, the tau particle, and 3 corresponding neutrinos. Electrons form the outer structure of atoms and participate in chemistry. Muons and tau particles resemble heavier relatives of the electron, although both are unstable. Neutrinos have no electric charge and interact only through the weak interaction and gravity, making them extremely difficult to detect. The quarks are known as up, down, charm, strange, top, and bottom. They carry a property called color charge and interact through the strong nuclear interaction. Quarks are not normally found alone. They combine into composite particles such as protons, neutrons, and many shorter-lived hadrons. Every quark and lepton has spin 1/2. As fermions, they obey the Pauli exclusion principle and Fermi-Dirac statistics. Identical particles of this kind cannot all occupy one identical quantum state. The particles associated with the fundamental interactions belong to a different category. The photon is the quantum of the electromagnetic field and is spin 1. Gluons carry the strong nuclear interaction between quarks and also have spin 1. The electrically charged weak bosons and the neutral weak boson are spin 1 particles responsible for the weak nuclear interaction. These particles are known as gauge bosons because they arise from gauge symmetries built into the Standard Model. They do not obey the exclusion principle in the same way as fermions. As bosons, many identical examples can occupy the same quantum state. This distinction between half-integer spin and integer spin reaches deeply into the structure of nature. Matter particles are fermions. The confirmed particles that mediate the Standard Model interactions are spin 1 bosons. The Higgs boson occupies another category. It has spin 0. The Higgs field extends throughout space, and interactions with this field help give masses to the electrically charged weak bosons and to elementary fermions. An excitation of the Higgs field appears as a Higgs boson. In 2012, experiments at the Large Hadron Collider at the European Organization for Nuclear Research announced the discovery of a new particle with a mass of roughly 125 billion electron volts. Finding a new particle at the expected mass was only the beginning. Researchers also had to determine whether its properties matched those predicted for the Higgs boson. The Toroidal Large Hadron Collider apparatus collaboration and the Compact Muon Solenoid collaboration studied the particle's production and decay patterns. They examined how its decay products were distributed, including their angular relationships. These measurements were important because particles with different spins produce different patterns. The results supported spin 0 and helped exclude several competing possibilities. Confirming the absence of intrinsic spin was therefore essential to identifying the new particle as consistent with the Higgs boson predicted by the Standard Model. Spin also applies to composite objects, although their total values may emerge from several contributions. A composite particle can contain the intrinsic spins of its constituents, angular momentum associated with their relative motion, and contributions from the fields binding them together. These different forms combine according to the rules of quantum angular momentum. The proton is a particularly important example. A proton has total spin 1/2, but it is not an elementary particle. Its simplest description contains 2 up quarks and 1 down quark. The full quantum structure is much richer, including gluons and temporary quark and antiquark contributions within the strongly interacting system. Early expectations suggested that the spins of the proton's quarks might account for nearly all of its total spin. Experiments showed that the situation is more complicated. The spins of quarks and antiquarks provide only part of the proton's angular momentum. Gluon spin and the orbital motion of quarks and gluons also contribute. Determining how these pieces combine into the proton's measured spin, 1/2 remains an active area of research in quantum chromodynamics, the theory of the strong nuclear interaction. The proton demonstrates why total spin does not always reveal a simple internal arrangement. A composite particle can have a precisely measured spin, even when that value emerges from a dynamic combination of quantum fields and constituent motion. Spin must also be distinguished from helicity. Helicity describes the relationship between a particle's spin and its direction of motion. It is often described as the component of spin along the momentum direction. For a massive particle, an observer moving faster than the particle could see its direction of motion reverse, while its spin orientation remains unchanged. The measured helicity would then reverse. This means helicity is not generally an observer-independent label for massive particles. Massless particles are different because no observer can move into their rest frame or overtake them. A photon always travels at the speed of light in a vacuum. Its physically permitted helicity states correspond to 2 opposite relationships between its angular momentum and direction of travel. This should not be pictured as a photon rotating like a tiny propeller. Photon helicity expresses how the electromagnetic quantum state transforms and how its polarization is related to motion. Chirality is connected to helicity, but is not identical to it in every situation. Chirality is a mathematical property describing how particle fields transform under the space-time symmetries of relativistic quantum theory. It plays a central role in the weak interaction, which treats left chiral and right chiral fields differently. For massless particles, chirality and helicity can be closely aligned. For massive particles, the relationship becomes more subtle. A particle may have a definite chirality within the theory, while helicity depends on the observer's frame of motion. The distinction matters because the weak interaction is chiral. It does not treat every mirror-reflected version of a process in the same way. This asymmetry is one of the most striking features of the Standard Model. A possible quantum particle associated with gravity is often called the graviton. In many proposed quantum theories of gravity, the graviton would be a massless spin 2 particle. This spin value reflects the transformation properties required for a quantum field resembling gravity. No graviton has ever been experimentally detected. It is not part of the experimentally confirmed Standard Model, and its existence remains hypothetical. Even so, the proposed spin 2 character shows how deeply spin is linked to the form of an interaction. Spin 0, spin 1/2, spin 1, and spin 2 are not merely numbers attached to particles after they have been discovered. They describe fundamentally different ways that quantum fields can respond to rotations and transformations of space-time. Spin classifies particles because it reveals the geometry of the fields from which those particles emerge. Quarks, leptons, gauge bosons, and the Higgs boson do not belong to different families because some are literally spinning faster than others. Their spin values express distinct quantum structures, each governed by its own transformation rules. What began as a misleading image of microscopic rotation has become one of the main organizing principles of fundamental physics, Spin began as a puzzling property inferred from atomic spectra and magnetic experiments. Today, physicists can prepare it, manipulate it, transport its influence through materials, and measure it with extraordinary precision. What once seemed like one of quantum mechanics' stranger complications has become a practical technological resource. Ordinary electronics mainly uses electric charge. Electrons are moved through circuits, accumulated in capacitors, and directed through transistors to represent and process information. Yet every electron also carries intrinsic spin and an associated magnetic moment. Spintronics is the field that uses this additional quantum property. The name combines spin with electronics, although the electrons are still not physically rotating like miniature flywheels. Spintronic devices exploit spin-dependent transport, magnetic order, and the different ways electrons move through materials depending on their quantum states. One of the most important early breakthroughs was giant magnetoresistance, independently discovered by Albert Fert and Peter Greenberg during the 1980s. The effect appears in structures containing extremely thin magnetic layers separated by a non-magnetic material. The electrical resistance depends strongly on the relative magnetic arrangement of those layers. When the magnetic regions are aligned in the same general direction, electrons with a favorable spin relationship may pass through the structure relatively easily. When neighboring magnetic layers point in opposing directions, more scattering occurs and the resistance increases. The word giant refers to the size of this resistance change compared with previously known magnetoresistive effects. The response was large enough to become technologically useful. Giant magnetoresistance transformed magnetic data storage. Information on a hard drive is stored through tiny magnetized regions representing different states. A read head must detect the weak magnetic fields produced by those regions as the disk passes beneath it. Using giant magnetoresistance, engineers created much more sensitive read heads. Smaller magnetic regions could be distinguished reliably, allowing more information to be packed onto the same physical area. This contributed to the rapid increase in hard drive capacity during the late 20th and early 21st centuries. Spin could do more than passively reveal a magnetic state. It could also help change one. An electric current passing through a magnetic material can become spin polarized, meaning that one spin orientation is represented more strongly than the other. When this current enters another magnetic region, angular momentum can be transferred from the moving electrons to the material's collective magnetic state. This process is called spin transfer torque. The transferred angular momentum can alter the orientation of magnetization, allowing an electric current to switch between magnetic states. Such methods support forms of non-volatile memory that retain stored information even when electrical power is removed. Spin has also become a possible carrier of quantum information. A quantum bit, commonly called a qubit, is a controllable quantum system with two computational basis states. A spin 1/2 system naturally provides two measurable alternatives along a chosen axis, making it an appealing candidate. The two basis states may be represented by spin up and spin down. Unlike an ordinary electronic bit, which is assigned either one classical state or the other, a spin qubit can enter a coherent superposition containing contributions from both possibilities. Several spin qubits can also become entangled. Their combined state may then contain correlations that cannot be reproduced by treating each qubit independently. Superposition and entanglement are among the resources that allow quantum computers to perform certain operations in ways unavailable to ordinary classical machines. Daniel Loss and David DiVincenzo proposed using individual electron spins confined within semiconductor quantum dots for quantum computation. A quantum dot is a tiny region in which an electron is trapped by carefully controlled electrical potentials. The confinement creates discrete energy states, causing the structure to behave in some respects like an artificial atom. Magnetic fields can separate the two spin states in energy. Precisely timed electromagnetic signals can then prepare superpositions and rotate the spin state through quantum state space. Nearby quantum dots may be coupled so that the spins of confined electrons influence one another, allowing operations involving more than one qubit. The idea is elegant, but constructing a reliable quantum processor from individual spins is extremely demanding. A useful spin qubit must remain coherent long enough for calculations to be completed. Coherence preserves the relative phase within a quantum superposition. Unwanted interactions with surrounding nuclei, electric fluctuations, thermal motion, and imperfections in the material can disturb the state. Researchers must also perform control operations with exceptional accuracy. A small error in the strength, timing, or phase of a pulse can leave the spin in the wrong state. When many operations are combined, these imperfections accumulate. Neighboring qubits must interact strongly enough to become entangled, but not so strongly that they can no longer be controlled separately. Finally, the state of each qubit must be read without introducing excessive disturbance elsewhere in the device. Several physical platforms are being explored. Electron spins in semiconductor quantum dots may be created using materials such as silicon. Silicon is especially attractive because carefully purified forms can contain very few nuclear spins, reducing one important source of decoherence. Donor atoms placed within silicon provide another approach. A phosphorus atom, for example, can contribute an electron whose spin and nuclear spin may be controlled and measured. These systems combine the established manufacturing knowledge of semiconductor technology with the precision required for quantum experiments. Defects in diamond provide a different platform. A nitrogen vacancy center forms when a nitrogen atom replaces a carbon atom next to an empty position in the diamond crystal. The defect contains controllable electronic spin states that can be prepared and read using light and microwaves. These diamond defects can retain useful quantum properties under relatively accessible conditions. They can also act as extremely small sensors because their spin states respond to nearby magnetic fields, electric fields, temperature changes, and strain within the crystal. Trapped atoms and ions offer another route. Electromagnetic fields can hold individual particles away from surrounding material, reducing environmental disturbance. Internal atomic states and spin-related degrees of freedom can then be manipulated using highly controlled laser pulses. Spin-based quantum sensors take advantage of the sensitivity of these states. A weak magnetic field slightly changes the rate at which a spin state evolves. By preparing a superposition, allowing it to accumulate phase, and then measuring it, researchers can infer the strength of the field. With carefully designed systems, spin sensors can investigate magnetic structures within materials, detect tiny electrical currents, examine individual molecules, and map conditions over distances approaching the scale of atoms. Diamond-based sensors have been used to study magnetic behavior in condensed matter and to detect changes in nearby chemical or biological environments. Nuclear spins may also serve as exceptionally stable memories or sensitive probes because they often interact more weakly with their surroundings than electron spins do. The practical value of spin comes from its unusual combination of stability and controllability. It is sufficiently protected to preserve quantum information for useful periods, yet sufficiently responsive to magnetic and electromagnetic fields to be manipulated and measured. None of these technologies works by grabbing an electron and twisting a microscopic surface. Engineers are not winding up tiny quantum toys and hoping they keep turning. They are controlling an intrinsic degree of freedom. Magnetic fields, electric potentials, material interactions, and carefully timed pulses alter the quantum state and the probabilities of future measurements. Spin became technologically useful, not despite being unlike ordinary rotation, but because its quantum nature provides properties classical spinning objects could never offer. The same non-spinning angular momentum that once confused atomic physicists can now read stored information, switch magnetic memory, sense extraordinarily weak fields, and encode the delicate states of experimental quantum computers. Quantum spin was never really spinning. It is a genuine form of intrinsic angular momentum, but it does not describe a particle rotating around a material axis. An electron has no known surface, no hidden equator, and no internal machinery turning beneath its charge. Spin belongs to the particle in the same fundamental sense as mass and electric charge. The path to that understanding began with ordinary angular momentum and the magnetic effects produced by moving charge. Atomic spectra then revealed patterns that classical physics could not explain. The anomalous Zeeman effect exposed a missing structure. Wolfgang Pauli introduced a classically indescribable two-valued property, and the Stern-Gerlach experiment showed that measured angular momentum components appear in discrete outcomes. George Eugene Uhlenbeck and Samuel Abraham Goudsmit recognized that the electron carried intrinsic angular momentum, although the early image of a rotating charged sphere soon proved impossible to maintain. A tiny classical sphere would need implausibly rapid motion to reproduce the electron's angular momentum and magnetic moment. Modern experiments also reveal no extended mechanical surface or internal parts. Physics therefore defines spin through quantum states, permitted measurement results, rotational symmetry, angular momentum conservation, and the transformation of relativistic quantum fields. Every electron has the same fixed spin magnitude. What changes is the result obtained when one component is measured along a chosen axis. A state definite vertically may be uncertain horizontally. Measurements along incompatible directions alter what can be predicted, while superposition allows several possible outcomes to contribute coherently to one quantum state. The Bloch sphere offers a useful map of those states, but its arrow is not a physical axle. Spin 1/2 particles behave even more strangely under rotation. A 360-degree transformation changes the sign of the spinor, while 720 degrees restores the complete quantum state. Paula Maurice Dirac gave spin its deeper relativistic foundation. His equation described spin 1/2 naturally, explained the electron's magnetic behavior, and led towards the prediction of antimatter and the positron. From there, spin reaches across matter. It helps create atomic fine structure and spectral fingerprints. Through the Pauli exclusion principle, it shapes electron shells, the periodic table, chemical bonding, and the stability of ordinary objects. It contributes to magnetism and to the quantum pressures and interactions supporting white dwarfs and neutron stars. Nuclear magnetic resonance and magnetic resonance imaging show that spin states can be prepared, changed, and measured with remarkable precision. Entangled spins reveal correlations tested through Bell inequalities, while spin values classify the fundamental particles of the standard model. These connections also show that spin is not merely a private label carried by one particle. It can be shared through entangled states, exchanged between systems, organized collectively across magnetic materials, and preserved or manipulated as information. Its effects can remain delicate at the quantum scale, while still building the solid and magnetic world around us. The same property now supports spintronics, quantum sensors, and experimental spin-based quantum computers. Spin appears mysterious, mainly when forced into the wrong classical picture. Once understood as an intrinsic quantum property describing how matter responds to rotations, its many scattered effects become parts of one coherent principle. Nothing inside the electron needs to turn, yet the universe still keeps perfect count of its angular momentum,